Good afternoon, everyone, and thanks for coming. We actually have quite a few human beings in the room here, which is nice, and of course a lot on Zoom as well. We have a series of two presentations, one this week and one next week, to highlight the two new detectors that we've got at ASU recently. And so today we're going to talk about the new detector and the capabilities of the ASU Nion Microscope. The Nion Microscope, for those of you that might not be so familiar with that, it's a scanning transmission electron microscope. So the idea there is that the electron beam is focused down to a small spot, typically 1 angstrom in size, about the dimensions of an atom, and then we scan the beam over the sample and we collect the scattered electrons to form images or to form diffraction patterns. And this is a photograph of the microscope over here. You're welcome to come and look at it in the Eyring Material Center whenever you want. The main advantages of this microscope is that it can perform imaging, STEM imaging at fairly low beam voltages. So that means it's very good for beam-sensitive materials, two-dimensional materials, nanoparticles, and soft materials. The other main feature about this microscope is that it has the best electron energy loss spectroscopy capability on campus. And especially with the new detector, it really allows us to do very fast elemental mapping. It allows us to probe electronic, phononic, and photonic modes. And using a technique called aloof beam spectroscopy, we're able to also probe organic and beam-sensitive materials. And so to tell you a little bit more about this, I'm going to hand the floor over to Shize.
So I'll basically introduce some technical details of the microscope. So the ASU Nion Microscope is equipped with a high brightness cold field emission gun, which offers a very decent atomic size probe with a size about 1 to 2 angstrom at a high current larger than 0.5 nanoampere. And the aberrations can be fixed up to the 5th order, and it operates at 3 different voltages of 30, 60, and 100 kV, which will be good for beam-sensitive materials. And in terms of the use capability, we can achieve as high as 8 millielectron volt at zero loss peak at 60 kV. With the new direct electron detector, we can do a lot of fancy techniques, such as the 4D stem, along with the normal hard-if, medium angle, annular dark field, and bright field imaging modes. With this particular microscope, we can do many different functions in terms of use. For example, the call loss, which is Syria, we can achieve decent energy resolution, which is comparable to the X-ray absorption to resolve the valence state of cerium atoms. And also with the low loss capability, we can measure the different phonon signal in different materials such as bromnitride, silicon oxide, and silicon carbide. Here are some examples that we can use the low electron beam voltage to image atomic structure. The material on the left is a 2D monolayer, which is tungsten, selenium, sulfur Janus monolayer from Photonic group at ASU. And the right image shows the platinum and copper alloy nanosheet, which is sampled from a Northern Arizona University Yakman group. So these images show that the microscope offers really good spatial resolution. Now, Peter Crozier will introduce the new detector.
So this detector, funded by a National Science Foundation MRI, is what's called a direct electron detector. And so I put together just a slide to illustrate what that is. Most of the detectors you have in electron microscopes today, the conventional detectors, are what are called indirect detectors. And by that, what that means is that the electrons, first of all, get converted to a photon signal. So the electrons go into the scintillating material. And then it's those photons that are actually transferred down to the camera element, if you will, the CCD array, similar to what you might have in your cell phone camera. So this photon conversion process reduces the overall efficiency. And also, as you can see from this cartoon, the photons tend to spread. And so that means that the point spread function of this detector is inferior. And so technically, the efficiency is described in terms, for those of you that know the detective quantum efficiency, and the point spread function is often technically described in terms of something called a modulation transfer function. Now, in the new detectors that are coming out now, we get rid of the photon conversion step. And so what we're able to do now is expose the sensors directly to the electron beam. And that means that we become much more sensitive, so much higher detector quantum efficiency and much better point spread function because we don't have this spreading of the photons. The particular architecture of the detector today for the Nion microscope is a so-called hybrid pixelated detector, and that is composed of a chip, a sensing chip, each one of the elements of the chip that are bonded to a readout chip underneath. And I won't go through all the technical details, but I just want to say that the detector that we'll talk about next week on the Titan microscope K3 detector is a different architecture, and there are different advantages and disadvantages to each system. But I just wanted to say a little bit about that right now. Again, for those of you that might be interested in some of the technical details, the detector is made by a company called Dectris. So here's a picture of it, pretty boring. This is the sensor element here. And again, a little bit of technical detail. This is a graph of the detector quantum efficiency as a function of spatial frequency. So going and normalized to the Nyquist frequency. So Nyquist is over here. The black dotted curve is the theoretically best achievable ideal DQE, detector quantum efficiency. So it starts at 1 for spatial frequencies of about 0, and it drops to about 0.4. Those of you that know the Nyquist is about 0.4 is the best you can get. What I want you to point out is that our microscope running at 30 or 60 kV, if you look at the yellow curve and the blue curve, they're almost matching the theoretical maximum. So the differences in efficiency that we have on our detector are on the order of less than 20% away from the theoretical maximum. So that's really fabulous performance. And then if you look over here at the modulation transfer function, the dotted black curve is the ideal modulation transfer function, again, plotted as a function of spatial frequency. And again, our microscope is the blue and the yellow and the dotted orange curve. And you can see that they're almost exactly following the theoretical limit. So that's one of the reasons why we're so excited about this detector, because it's really as close to an ideal detector as you could probably expect to get. Just to show you some practical things, and Shize will show you more examples, but in terms of electron energy loss spectroscopy, this is an example that illustrates the improvement in the sensitivity, the improvement in the DQE, and in the point spread function. So this is a valence loss spectrum from cerium oxide, showing photonic modes. These are photonic modes. This is the band gap is about here. These are photonic modes that you can see. The red spectrum was recorded with the old detector, and you can see that it's noisy. It took 200 seconds to record. The blue curve is recorded with the new detector, and you can see that it's a lot less noisy and the acquisition time is less. So that's telling us that, we're getting much more sensitivity. But the other thing I want you to notice is that the peaks are much sharper than the red curve. It's exactly the same area of the sample. The peaks are much sharper. That's because the point spread function of this detector is much better. So you get much better quality spectra. And you might say, well, here it doesn't make much difference. But if you look at this part of the spectrum, we're really starting to see things now that we couldn't see before, right? So this is what's great. The other thing about this detector, which is great, for those of you that know about spectroscopy, the electron energy loss spectrum typically spans about 7 orders of magnitude in terms of intensity. And usually most of our old detectors could only span 3 or 4 orders of magnitude. So we would have to record the spectrum in separate chunks. Now we can record the entire spectrum in one go and capture the entire dynamic range without any saturation effects at all. And again, that's going to, for a lot of applications like elemental mapping, that's really going to be fabulous. So I'm going to hand you back to Shize, who will go through a few more examples.
Okay, here's an example about fast elemental mapping at atomic resolution. On the left side of the slide is an example that we took on the ASU microscope from a strontium titanium oxide sample. So the mapping only takes 30 seconds, and we can resolve chemical from the strontium and titanium in the atomic resolution. And on the right is from a report by the company selling the detector. So they are also reporting similar kind of SDO results. Then we can measure electronic excitation like excitons in a sodium chloride. And on the left is a ADF image showing a sodium chloride cube. And we can use aloof beam EUs to measure the exciton signal from the cube. You know that sodium chloride is very beam sensitive, and the aloof technique provides a unique way to reduce beam damage and probe electronic structure. Then another example is that we can probe plasmons. On the left is a movie showing that we can use electron beam to produce sodium nanoparticles supported on sodium chloride cube. And then we can use EU's mapping to probe the spatial distribution of different plasma modes in real space. Here is another example that we can measure the photonic modes in serial nanocubes. On the left shows an image of the serial cube with about 200 nanometers in size. And we can park the beam at different positions outside the cube, marked as face and edge. And then if you look at the spectrum to the right, you can see that the electron beam can exact and probe different modes when the beam is parked at different positions. And that means local coupling can be probed with the EU's technique. Here is another example that we can study soft and biological materials. The image shows two different protein samples. If you look at the spectrum, that you can see that they can be distinguished from the vibrational signal from the low-loss EUs, which means high spatial resolution probe can be provided, which is similar to IR. This offers a unique technique for nanoscale soft material study. And then with the new detector, we can also collect the diffraction pattern at each pixel from the material. This image shows a normal annular dark field image. And while scanning to collect the image, we can record the diffraction pattern, which is shown here at each pixel. And then we can reconstruct useful information from the diffraction pattern. For example, this image to the right shows the reconstructed phase image, which can be used to show very high spatial resolution and contrast related to the atomic structures. Now, Peter Crozier will talk about some experience about using the Nion microscope.
So the question is, how can you use this to benefit your research program? So there's several things that Shize will be doing with, and I'll be helping. Of course, Shize is available to consult with you on what this microscope is able to do, and I'm happy to help out as well with that. So consultation services so that you can figure out whether or not a problem that you have could be perhaps solved with the techniques that Shize has available on the microscope. He can do short proof of concept demonstrations to groups that don't have experience with microscopy. So we're talking like 1 to 2 hours here, not like 2 weeks worth of work, so that perhaps you can justify doing more work on the microscope in the future. And one of the things about this microscope is it's still very rare. There's not many universities in the world that have this. And so that's a big advantage to faculty for writing proposals. If you can include some of these capabilities in your proposals, it will make your proposal much more competitive and will increase the probability of getting funding. Shize and I will write a 1 or 2 page description of some of the technical capabilities so that you can copy and paste that into your proposals. And of course, we're happy to also edit and read sections of your proposal that might mention this microscope. So that's one way in which we can help benefit your research. And then the second thing we just wanted to cover was, how do you get data off this microscope? If you have some TEM experience in your group, then it would probably be good to have a student or postdoc trained. Shize offers training on the microscope. There are different levels of training. So basic STEM and basic elemental mapping is relatively easy. Someone could learn how to do that in 1 or 2 sessions. The monochromated eels, that's, for example, the vibrational eels, is a little bit more difficult, and the 4D STEM is a little bit more difficult, so you would probably have to spend a bit more time in that. But for those of you that have been familiar with this microscope since its installation, it's much more stable than it was in the early days and much more robust, and so we feel that it's much more solid in terms of supporting your research. If you're new to TEM, as I say, short projects, I would suggest, work directly with Shize. He can assist in data acquisition and then have a student or postdoc he can mentor the student or postdoc in doing the data processing, because of course it takes time to process the data. For longer projects, if you don't want to invest the time in training someone in your group, then you might want to consider a collaboration with some of the local TEM experts, Shize, myself, David Smith, Peter Rez, Ray Carpenter, etc., if you don't want to invest the time and effort on doing it yourself. We're going to go straight into questions. We wanted to keep the presentation short, and we're happy to answer any questions that any of you have here. Maybe we can take questions from the room first of all, and then we'll take the questions from the Zoom.
I have a question. So in terms of yields, what's going to be the spatial resolution and the spectral resolution for this TM?
So the spatial resolution will be defined by the probe size. So we can achieve better than 1 angstrom easily at 100 keV. If you lower the voltage, the spatial resolution will be slightly worse.
It also depends what you want to do. So it's probe size limited for elemental mapping, but as you go down to the optical regime, then you get delocalization effects. And so I would say, depending on what you're trying to do and what mode you're running, and if you're running in, say, the aloof mode where you part the beam outside, the spatial resolution is about 20 nanometers. If you're running in transmission mode, the spatial resolution is anywhere from 50 nanometers down to 1 angstrom, depending on how you set things up.
I see.
Yeah.
That's pretty good.
Yeah.
I think I would be interested in look at photonic modes. So more importantly is care about the spectral resolution. So
Right.
What's going to be the spectral resolution for the line?
Energy resolution. Yeah.
So the
Can you repeat the question for the online people?
Oh, yeah, sorry. Yeah. The question was, well, the first question was about spatial resolution. The second question was, what's the energy resolution?
Okay, so the energy resolution also depends on the operating voltage. So for example, we usually operate at 60 keV. At this voltage, we have an energy resolution of 8 millielectron volt. Yeah, that's the energy resolution.
So how about if we operate like 120 kV?
We cannot operate at 120 kV. We operate at 30, 60, and 100.
100 is highest. So if we operate at 100, what's going to be the resolution for that?
That can be around 10 to 12 millielectron volts.
So the question is, was the modulation transfer function graph from our particular system? No, it was done at the factory on their prototype, but our system performance is identical to the factory prototype. Let me see, the next question is, okay, someone's got a question here about eels in the ARM. We often had issues with thickness, which the AM requires thickness less than 100 nanometers. I believe that the limitation still remains true for the Nion. My primary interest is ion oxidation state. Yeah, so thickness is always an issue, depending on how the sample is prepared. Your sample typically needs to be 50 to 100 nanometers in thickness. But it's also very dependent on the form of your sample. If you have things like nanoparticles, then it's usually easy to go on the edge of the nanoparticle. Or if you want to do the so-called aloof beam technique, which we showed some of the vibrational spectra for, that's where the beam's actually outside the sample, then we don't really, the thickness is, you're not going through the sample, you're going adjacent to the sample. And so then that technique is much more forgiving of thick samples. What you give up then is spatial resolution though. Oh, there's a question from Tom Sharp. For core loss applications like iron valence state, how does the Nion compare to the Titan and its new detector?
I think the major difference is the operating voltage. So the Titan microscope operates at 300 keV. It offers a better tolerance to the sample thickness, but in the same time, 300 keV damage the metal badly, so you can damage your sample. In the Nion microscope, you can operate at 100 keV. Your sample is not damaged as much, but you are more sensitive to the sample thickness. So this is the balance, yeah.
Okay, well, listen, thank you all very much for joining us. So thank you very much.